long device, so that propagation of the wave, you really need to take the phase relationship into considerations. So last week, we talked about the strategy we're using is to dissect a very long transmission line into many short segments. And for each segment, we can come up with an equivalent circuitry model using lumped element circuits. For example, we have resistor per unit length and multiplied by differential length Z, inductor, capacitor, and the leakage resistance. Okay, so this is called the conductance. So today we're going to try to really write out the mathematical formulas. So in the end, we can solve for everything on the transmission line. So this figure is the same as shown in your slide number 11. So you can look at your slide. It's larger, more clear. But we have voltage and current at the input of one segment. At output, we also have voltage and the current. The only difference is the space is now having a slight differential length, delta Z. Okay, that's it. So at this moment, you have to think, where should we start? All that we know from last semester is, you still remember what this is called? Kirchhoff's voltage law, right? That's all we know. And there's another law called the Kirchhoff's current law, which we will use later. All right. So let's raise the blackboard so I can write better. The first mathematical equation we can use is Kirchhoff's voltage law. For this circuitry, somehow VZ of t is related to VZ plus delta Z with some relationship. But we already know the current as well. That's an unknown. Okay. So I can write V of ZT. This is my starting point. As I travel along with a voltage wave on the transmission line, I suffer from some kind of voltage losses. So the first loss is due to the resistor. That's my first voltage loss. And then I encounter the inductor. I suffer again another voltage loss. You have to remember how to formulate the voltage loss due to an inductor. After suffering two voltage losses, I come to meet the output of my small differential segment. So that voltage has to be equal to Z plus delta Z, and as a function of time. Okay. So that's my first equation, right? I can do some regrouping, right? Voltage and voltage, current and current. I want to classify them onto both sides. Okay, so let's do it. I'm moving this guy to the right, and then I divide it by delta Z. Okay, I'm moving this delta Z's to the denominator. Negative So that's my first equation. Okay, these two are the same. I'm only moving things around. But when you take a look, because our working principle is to assume this differential length is very, very short. So this thing on the left becomes a differentiation in space. So if I assume delta z is really small, this entire equation becomes del v del z equals negative r prime by z t plus l prime I. Okay. So this is not very surprising because differential equation in space means I'm trying to track the changes of my voltage as a function of space. Differentiation means the distance is very short. So even though in a very short distance, I will have changes in my voltage. And the reasonable changes are due to resistor loss and due to inductor loss. Okay, that's it. At this moment, can I really don't like to work in the time domain because in the time domain you have partial differential equation. So can I convert this equation into a frequency domain using phasor notation? So I can have, using phasor, dV, dZ. Now, in the phasor notation, voltage is only a function of space. You no longer see the time dependence. Okay? So the beauty of converting the same equation into the phasor domain is now you don't have partial differentials, but because you remember, if you have a partial differential in time, you multiply by j omega. So this is the equation I want to somehow relate voltage, change, and current. Okay, so this is the first equation that we finally wrote down. Okay, one down, one to go. We also need to know current, how to formulate current as a function of space and eventually time. So the second equation, the starting point, is what we've already used, KVL, Kirchhoff's voltage law. The second thing we learned in electric circuit is Kirchhoff's current law, right? So let's use KCL. KCL states for any node, all the currents adds up to 0. So let's look at this circuitry. I have one current coming in. I have one current coming out, second current flowing across the two metallic conductor, and the third current flowing across the capacitor. So the way to write this one is this is my input current. It will be split into 3 different branches. The first branch is the easy one, is my output current. Okay. I also have another current branch, which is leakage current. Z. So the third range is the current flowing across the capacitor. Right? Again, I'm using the same mathematical strategy. I'm moving the voltage to one side and current to the one side. All right, so I have and again, I can assume this delta Z is very, very short. So this becomes, I'm lazy. Let me assuming delta Z is approaching to 0. So let me just erase this one. Just 2 minutes. So delta Z is approaching to 0. So this becomes del I del Z equals, yeah, that's it. Again, I really don't like to work in the time domain. So in the phasor notation, transforming to phasor, this becomes di phasor as a function of Z only, dZ is equal to simple and elegant, right? So with the help of Kirchhoff's voltage and current laws, I came up with 2 simple equations. But when you take a look at the 2 equations circled by yellow, I'm trying to, for one equation, I'm trying to solve the differential change in voltage. But that voltage as a function of space is somehow related to the current as a function of space. The second equation is telling you a very similar thing. The current as a function of space is somehow governed by voltage as a function of space. So up to now, even though I wrote down 2 equations, I don't really know how to solve them together because voltage and current and voltage, they are somehow coupled together. So I don't really know how to solve them. So what can we do now? What is a typical mathematical strategy that we have learned in the past? When we have 2 equations, each equation is having 2 parameters and they are coupled together. What can we do? Can we perform another differentiation so that somehow the equation, the unknown to be solved on the left-hand side and on the right-hand side of the equality sign is the same? So that's what I want to do. Can I perform another differentiation in space to both equations? Okay. If I perform differentiation in space to both equations, I would come up with E squared voltage Z squared Okay, so this is what we have after performing another spatial derivative to both equations. But the beauty is, do I know this already? After another differentiation in space, the IZ initially on the right from my KPL equation is now picking up a differentiation. But that differentiation is known from my KCL equation, right? So the beauty is, now I can link, or I can replace this current relationship by voltage. For my second equation, I have current on the left-hand side, and I have initially some voltage as a function of space, but by replacing this with this, okay, I can have current. So let me rewrite this. Okay, so this is going to be slightly messy, but I hope you can really see it. Is it clear? Okay. So students, can you really differentiate what I'm writing down?
Yes.
Okay, all right. So I want to replace this one with this, okay? And the bottom one surrounded by yellow with this one, okay? So I will have okay, slightly messy, but I'm very happy with the result because in the end, now I realize this is just a form of a traveling wave. For the voltage, if you still remember from the first step of the part plane, voltage as a function of space is now performing a twice differentiation in space, and somehow that is equal to itself, linked through some kind of, well, constant. Current is doing the same thing. A second order differentiation in space, somehow linked to itself. Okay, so this is a very nice result. So if I can rename this very messy stuff, if I can define this gamma is defined as square root of the messy perimeter before the variables. Okay. After defining this gamma, then I have the equations as e squared b c squared minus gamma squared b z equals to 0. So that's the first one. So now it's very simplified and clear. Right? This is really, really a traveling voltage. And that constant tells you some kind of physical meanings, which we will come back later. And the second equation is now telling you, on the transmission line, you also have a traveling current wave. Okay. So after all the mathematical derivations, we come up with two quite simplified equations. And just by looking at it, and if you compare it to the wave equation I showed you in the first part from set, there's no doubt that voltage and current are both traveling waves on a transmission line, which is anticipated because if we want to deliver power on the transmission line, we need to have the energies in the form of a traveling wave. Okay, that's what transmission lines do. They send out and deliver powers in the form of waves. All right. So another definition, probably very important up to this point, is this gamma. What is its physical meaning? This gamma, well, if you look at inside, right, you have R and G, these are real values. But here you have J omega, so that's complex, right, imaginary. So when you multiply this whole thing together and take the square root, you will have some kind of the real part and an imaginary part. So that beta is not a known. It's not entirely new. Last Wednesday, we spent a lot of time deriving the mathematical form of beta. So this is alpha plus j 2 pi divided by lambda. Okay. This is the propagation constant we talked about last Wednesday. Having the alpha is going to give you some kind of attenuation. Okay? So I will write down the mathematical solution form for you. So the voltage phasor as a function of space. Because this is a very familiar wave equation. We know its solution form immediately, exponential functions. Pay special attention to the signs. If you still remember, last Wednesday, we spent a lot of time talking about the sign corresponding to the traveling direction. So V0 plus means I have a positive propagating wave. Meaning in this figure, positive means a wave is traveling from the left to the right. Okay, so this is defined as a positive propagation direction. If I have a wave propagating from the right to the left, this is defined as a negative propagation wave. Okay? So I can see as I'm walking around on the stage, people are working very hard. So let me walk slowly. Okay. We have a total of 4 cameras. Okay. Let me write out explicitly for you. Okay. So the colors correspond to the sign. So if I have a negative propagating voltage wave with an amplitude of V0 negative, remember propagating into the negative Z direction picks up a positive sign. Okay. So now I'm writing out explicitly the definition of gamma. if I have, for example, for the positive propagating wave, Z, okay. I look at the white part. I have a forward propagating wave, right? Starting with an initial amplitude, V0 plus, and propagating into the positive Z direction. As I propagate, the real part of gamma is going to attenuate this wave in its amplitude, right? Because exponential negative alpha Z means I have an exponential decay. So basically, gamma is called the complex propagation constant. It's complex because the real part defines how fast the wave is attenuated due to loss. Where does the loss come from? The real part is determined by the resistance and the conductance. What does resistors do? They transform wave energies into thermal energies. So they are the source of loss. Okay. So if we don't have resistor and conductance, then this gamma is becoming purely imaginary. So you don't have loss. Okay. So are we clear up to now? This propagation constant is becoming complex, and the real part gives you loss because we included the potential chances to have resistors and conductance. Okay? And they are the origins of loss. So it is not surprising we will have loss whenever we have resistors and conductance. All right? Okay, so I of Z is equal to I0. Again, we can have forward propagating current wave and backward propagating current wave. Okay, so they're both permitted. So at this point, how many unknowns do we need to solve in order to completely understand what's going on in the transmission? How many unknowns do we need to solve? Okay, we write this one. Looking at the solution forms, we have V0 plus minus, meaning the positive voltage amplitude, and the negative propagating voltage amplitude. And we also have another two, I0 plus and minus. So in total, we have 4 unknowns to be solved. If we know the amplitudes, these 4 amplitudes, ideally, we know everything on the transmission. But then the question is it really possible to solve all 4 unknowns? The mathematical skill and knowledge we accumulated up to now is, if we have 1 unknown, we need to write down 1 equation. Right? So if we have 2 unknowns, we need to have 2 equations forming a set. So if we have 4 unknowns, we need to write down 4 equation sets. that's quite impossible because up to now, we only know KVL and KCL. So starting from the very initial point, we're limited to write down two equations, right? First one, KVL tells you this one. Second one, KCL tells you this one. So we can only write down two equations. The number of equations is at most equal to the number of unknowns to be solved. So we are reaching a dead end. We have 4 unknowns, but we're only capable of writing down 2 equations. So what can we do now? This is a challenge. So is there anyone watching online wishing to answer this question? No one?
No one answered.
No one answered. Ah, it's too bad. But this is anticipated. All right. So now it's time to really think. Okay? But let me try to refresh your memory. As you think, let's go over this entire thing up to now. Okay? So I'm using the PowerPoint. So initially, we have the equivalent circuit model, and we wrote down KVL, KCL equations. Okay. So in the phasor domain, we simplified things. Okay. So we don't like to work with differential equations. So in the phasor notation, we have very beautiful multiplication. Okay. And then eventually, we didn't know how to solve this one because on the left-hand side, voltage, current. So we performed another differentiation. So now we can replace the IDZ with a former equation. So now we have this. So we proved up to now both voltage and current are traveling waves on the transmission line. And then somehow we define this gamma, right? This complicated stuff is actually telling you how the wave is propagating on the transmission line. Now, if you really want to ask yourselves the physical meanings of gamma, loss, and the effective wavelength, beta is 2 pi divided by lambda. So this tells you, even though you have the same operational frequency, but if you're working on 2 different transmission lines, the attenuation coefficient and the effective wavelength will be very different. Okay? So for a given transmission line, you would have its own resistance, inductance, conductance, and capacitance. So all these 4 parameters is simplified and gathered to give you a sense of how fast the voltage and current are attenuated and what are their resulting wavelength. The wavelength can be very different as compared to the same frequency wave traveling in vacuum. Okay. Now, another physical sense. Even though we have 4 unknowns, V0 plus, V0 minus, I0 plus, I0 minus, which we don't know how to solve for now, but there is one happy thing. What is that happy thing? There's one happy thing embedded in this equation. No matter how its voltage or current, positively propagating or negatively propagating, they are all having the same propagation behavior. They share the same gamma value. So this is telling you voltage and current, they have the same attenuation coefficient, and they have the same effective wavelength on the transmission line. right? So this gap is very important. Once you have a well-defined transmission line, it tells you the voltage and current are actually traveling at the same speed, traveling with the same wavelength. They're traveling with the same attenuation, no matter which direction they're traveling. This applies both to current, voltage, positive propagating, and negative propagating. Okay? So this is the only nice thing that we can up to now. Right? So these two equation sets tell you counter-propagating waves are allowed. You can have forward propagating and backward propagating. This means the transmission line can be used for bidirectional communications. This is also nice, right? So if you have a transmission line, the power can be delivered from the source to the user. The user can also somehow donate energy back to the source. Okay. Second physical meaning is, just as I said, counter-propagating waves, no matter its voltage or current, they have the same propagation constant. So that's nice. If the forward propagating wave and the negative propagating wave can have different propagation constants, that's too messy, right? And it's impractical and physical, right? So now we are in the process of simplification and reducing the number of unknowns. So let me plot a line. So reducing the number of unknowns. Starting from now on, it might be purely mathematical, but I'm trying to turn the mathematical derivations to really physical senses, okay? But the overall target is we have 4 number of unknowns, which is unsolvable, but eventually we can understand what is happening on the transmission line. But that requires mathematical skill and more physical understandings, right? So let me ask you one question. I want to perform some kind of definitions. I want to define some more variables to help me reduce the number of unknowns. Does that sound reasonable? I'm introducing one more stuff, and that could help me reduce the number of unknowns. Sounds like a contradiction, but that's what happens in engineering. Usually you introduce more complexity, you gain more functionality. Right? Okay. So what I want to do now is I want to introduce a new variable called characteristic impedance, 特征阻抗, characteristic impedance Z0, hoping that it might help me reduce the number of unknowns. So Z0 is really trying to ask, okay, from above, we learned that on the same transmission line, voltage and current, no matter forward propagating or negatively propagating, they have the same wave behaviors. They have the same loss, they have the same effective wavelength. So the question is, V0, I0, voltage and current, they're divided into forward and backward. are they really different? If they're not really that different, then I can somehow simplify them and reduce the number of unknowns by half. So I can start with 4, and I come up with 2. So the question is, if I define impedance by definition is voltage divided by current, just like resistance. But when you have a complicated circuitry, you have RLC, you have impedance, right? This is the formal definition. Voltage divided by current is impedance. So what if I try to define the forward propagating voltage amplitude divided by the forward propagating current amplitude? That gives me some kind of impedance value, which is completely determined by the transmission line. Then I might have the possibility to reduce the numbers of unknowns. Okay? Now, at this moment, you might also want to guess, is it possible that V0 minus divided by I0 minus is also equal to that? Take a guess. But can you see what I'm trying to do? If voltage and current amplitudes are somehow linked together through a constant, then that constant is provided by the transmission line. Once you have a defined transmission line, it already satisfies voltage and current is obeying some kind of specific situation or value, then you don't really view this as a new variable, right? If this is true, you only have V0 plus and V0 minus. I0 plus, I0 minus are actually known, right? So that's a thinking. So the thinking is, by introducing characteristic impedance, can I reduce the number of unknowns to only 2? Of course, this remains a big question mark. We don't know up to that. Okay? But if it works, immediately the number of unknowns is reduced from 4 to 2, which is more solvable. Okay, so do we agree up to now? Do you understand my physical flow? The process flow is trying to define some kind of intrinsic parameter determined by the transmission line structure. And then I can view current as voltage, but having only a linear relationship. If you multiply the voltage by some constant and you have the current, then you only have to worry about solving voltages or only solving the currents. Okay? In the end, you only want to solve for 2 unknowns. Okay, so if that is my goal, where should I start? Where should I start? This is the position I should start. This is the generalized solution form, right? I have the wave equations, and I have the solution forms. If I have the solution forms, I should start from there and try to really find my solutions. Okay, so where do I start? From here, somehow write V, Z. This is tricky. I have the generalized solution form, and I really want to rewrite it so I can really solve for the unknown parameters. Can I do this? Can I do this? Voltage phasor as a function of space can take on a forward propagating solution and a backward propagating solution. Can I say that, well, I only care about the total voltage. So even though on the transmission line, I have forward and backward, but when I add them together, they're also a solution for it, right? Superposition. When one of the component is a solution to the wave equation, I add them up linearly. This is called linear superposition. The result is still a solution to the initial wave equation. So this is valid. And this is really saying that on the transmission line, at the same time, simultaneously, I have forward propagating wave plus a negatively propagating wave, which is completely valid. Okay. I of Z can also have forward propagating component and backward propagating component. Are we really happy here? All right, so these are the really generalized solution form on the transmission line. What can I do? Let's come back. Let's come back to the initial two equations. The one derived from KVL, the one derived from KCL. These two are very important. These are the starting equations. Initially, we didn't like them because on one side, I have voltage, which is to be solved. But on the other side, I have current, also to be solved. So initially, I didn't like these two equations. Different parameters on different sides of the equation, we don't like them. But now, for this purpose, we will try to like them, okay? Because if I perform differentiation in space to B using that generalized solution form, I can immediately link to the current mathematical formula. So let's try to do it. Let's try to perform one spatial derivative, and then we somehow combine and look at the resulting relationship, and then we can define the current amplitudes. So if I have enough space, okay, so dV of Z dZ equals, I'm really trying to perform the differentiation. Negative gamma plus gamma V negative. I hope this is fine for you. Can you still read this letters clearly? So after performing spatial derivative to the generalized solution form for the voltage, don't ever forget that is equal to something we already know in the form of current. Negative R prime plus J omega L prime IZ. IZ. IZ is this one. Right? So let's come back. Or just let me try to come back to the equation. Do I have the equation on the PowerPoint? Yeah, this one. Right. So dV/dz equals negative something current. So all I'm trying to do is I'm using my solution form, and I'm using the solution form, right? Counterpropagating waves, perform its spatial derivative, and that would be equal to the negative of this one, solution form of I. Okay, so this is what we have. I performed the spatial derivative. This is what I have. And that is equal to negative r prime plus j omega L prime and multiplied by my current generalized solution form. And now I can do turn-by-turn comparison. The ones with exponential negative gamma z should be compared with their corresponding amplitudes. The ones with positive exponential gamma z should be compared. All right. So I can see even the TA and the video filming staffs are tired. So let's take a 10 minutes recess and come back. But during this 10 minutes, try to write down the further definitions or the relationships using characteristic impedance. Okay, let's see you back in 10 minutes.
如果你要报这个节目，你就尽量不要报到这个，管得很。
买的是同一支。
就是正常来说，你把它正的话，就是它会照到旁边。如果照到旁边的话，太亮，它就会整个
哦，所以就是你说黑板不要看到左边的，
对，就是你要尽量卡掉，尽量不要看。
有一个问那个 hate
对啊，
老师有人问一个那个 hate
有
什么意思？
问说就是上面那个 I 跟 V 上面那个 hat 的，
哦，那代表 phasor。
那你回答他。
现在还在。
对，他还在。
I 跟 V 上面有一个小三角形，是代表这 phasor notation， 所以这样你们会比较明显的可以看到说是在 frequency domain， 所以只要是 time domain 都是小写。那在 frequency domain 会大写，然后为了大写，我再加一个 hat， 就让你知道是在 phasor notation。OK， 好，谢谢问问。
我是有，但是我没有带，要大概这么高的。
对啊，因为这样子你比较好弄。
这样。
它是左右相关的。谢谢老师，不客气。我平常有课的。
是我的。
然后自己记得。
用这样会比较好。
对，因为有时候我们下次可以带老师。
对啊，换我们下次一次。
我在想他可不可以接两个镜头，然后这边的头就切这边。
真的可以来回在一起。
对，跟你买的一样。我还没有研究过怎么切它，而且如果要的话，要去再买一个那个
hub。
对对对， 因为我这边只有一个 USB。
这个你就留着。
对，
因为这样子你就不用比了，就只是切那个球，你这样子的刚刚全。
我说再看看你们。
你们看到3个，
我还有，我可以
因为有3个3区，
我可以再定一下。
我先试试看能不能切。
研究看看。
这个小孩可能让他做。
这个很亮，就是对比太强了。
反正重点是要你先把这个清楚。
因为它很大的面积，所以它不能接到入上。
哦，你那边是什么？
对，它这样会简单多一点。
建议进去走路上打，
我不知道。
是的。
question from the student. What does the hat means? So whenever I write a capitalized letter with this triangle called hat, it means I'm writing the parameter in the frequency domain using phasor representation. Okay, so I tend to use lowercase letters like this one, lowercase I, lowercase b, to represent the parameter in the time domain. But after I transform to the phasor representation into the frequency domain, I like to use capitalized letters and then to add the hat to more pronouncedly state it's working in the frequency domain. I'm walking back anyhow. All right, so let's continue. So eventually, we performed the real spatial derivative for the generalized solution form, and I can link that to the KBL equation. Now I can compare turn by turn. The yellow ones, they are equal. The green ones are equal. So I now have these two relationships. So somehow, voltage amplitude in the positive direction is related to the current amplitude in the positive direction and is linked by the complex propagation constant and this resistance inductance. So basically, whenever you determine the working frequency, this is a constant. So this is telling you, once you know V0 plus, you already know I0 plus. By the same meaning, when you know V0 minus, the backward propagating voltage amplitude on the transmission line, once you know the parameters of your transmission line, you know its corresponding backward propagating current amplitude. So this is a very beautiful message. This is telling you after we take more detailed examinations, initially we thought we need to solve for 4 unknowns, but eventually we only have 2 unknowns to be solved. Once you know voltage, you know current. Okay? Provided that you really understand your transmission line. So if you know your gamma, basically you know how voltage and current are related for a certain direction. Okay? So this is the beauty of a transmission line. So let's take a look. I performed detailed derivation for you. So from the first equation, I can have V0 plus divided by I0 plus. This is what I intended to define because V divided by I is your impedance. Okay? So now from this, I can have V0 plus divided by I0 plus, which should be my forward propagating characteristic impedance. This, after some messy derivation, I have basically a pretty nice result. Square root of R prime plus J omega L prime divided by G prime plus J omega C prime. Okay. Now the bigger question is, what about V0 minus divided by I0 minus, right? If they're equal, then we hit the jackpot. So eventually, after the derivation, remember, there is an additional negative sign, but the value is the same, only differing in the sign. Okay, so which is really not too bad. Okay, so let's define this as Z0 and define this as negative Z0. Now you have to think. How can impedance take a negative sign? So what I'm saying is, on the transmission line, okay, the same transmission line, the ratio of V0 plus to I0 plus will be equal to Z0. So these are also determined, provided by the transmission line. For a transmission line, you have to know R prime, L prime, G prime, and C prime. So after you know all these four, 1, 2, 3, 4, you know all these four parameters, you know gamma. You know the complex propagation constant. And also, once you know these four parameters, you know the characteristic impedance. Okay? So for a given problem, those will be provided for you. Z0 probably provided for you. Gamma probably provided for you. And once you know gamma and Z0, you know basically everything for transmission. And once you know that, and if you know voltage amplitude, you know the current amplitude. Okay? So you only have the voltage amplitudes remaining to be solved. But now the issue is the positive voltage divided by the positive current amplitudes is indeed the characteristic impedance. It's provided for you. It's a transmission line parameter. But how can the negative propagating wave, the negative voltage amplitude divided by the negative current amplitude, is picking up the same value but with a negative sign? How can you explain this? I mean, or do you accept it? Do you embrace it? Just like I told you? I mean, having a negative sign is fine. Do you think it's fine? So this is really saying that I0 plus is V0 plus divided by Z0. I0 negative, I0 minus is negative V0 minus divided by V0, Z0, sorry. So remember, if you can accept voltage divided by current is taking on a negative sign, then the generalized solution form is now written in these two equations. Okay, voltage remains the same, but current is represented again by voltage. But you only have to divide by 0. But remember, for the negative propagating current wave, you have a negative sign. So let's talk about what's the reason behind this negative sign. One potential reason, very evident reason, is Professor Huang did it wrong. I made a mistake. Okay, and it should be. But what if I'm not wrong? What does the negative sign mean? So this is telling you I0 plus is equal to V0 plus divided by Z0, and I0 negative, the negative current amplitude, is the negative of V0 negative Z0. While you are thinking, does it make sense for us to ask, why do we have a negative propagating wave on the transmission line? Now, if we understand that, we will understand the significance of the negative sign. So the question now is converted to where does the negative propagating wave come from? So let me show you the transmission line. Right? So we have a transmission line. I have a very long transmission line. I have my user at Tsinghua University. High power is generating the power from some kind of dam. Okay. After the generation of power, they deliver to us through a very long transmission. So ideally, high power only wants to deliver the power to us, right? So ideally, on the transmission line, I should only have the forward propagating voltage and current. So how can there be backward propagating wave in the form of voltage and current? It is because we, the users, are very naughty. We never listen to teachers, right? When teachers send in the information, the knowledge, we usually don't absorb them. We bounce them back, like what you're doing now. Right? The TA is laughing. He's also my graduate student. Think of the delivery of energy on the transmission line as I'm trying to teach knowledge to you. The best situation of the student a teacher could ever dream of. I send in knowledge, I teach you knowledge, and you completely absorb the things I teach. In that case, the transmission line has only forward propagating wave. But you might be sleeping, right? You might be sleeping now, so my knowledge to you are somehow bounced back and returned to me. So as I'm teaching myself. I'm understanding the transmission line more and more. Each year, I'm better and better. Is that the situation? There's no response, so 100% absorbed. There's only forward propagating knowledge in our class. Yeah. So the reason is you might have the so-called impedance mismatch. The transmission line is represented by its characteristic impedance. For example, might be example Z0 equals 50 ohms. This is a very particular transmission line. So I have a 50 ohm characteristic impedance transmission line connected to a 100 ohm load. 50 does not equal to 100. So partially, some of the voltage, some of the current, and some of the power are reflected back. So therefore, you have input forward propagating waves, and you can also have a backward reflected wave. So that's a physical origin of having V0 plus, V0 minus. So now that we understand this, can we understand the sign to the characteristic impedance for the backward propagating wave? V0 minus divided by I0 minus is equal to negative Z0. Can any student try to answer this? If you get it right, you can have maybe 1 or 2 points for the semester score. This is a bonus. Can anyone try to explain this? Impedance, taking a negative sign. Well, impedance can be complex. So -1 means you have a 180-degree phase difference. So it is valid, but the physical meaning is, if you want to understand the physical meaning, are there any response? No response? Okay, we missed the chance to have bonus. Does anyone still remember P? Power. How is power related to voltage and current? Filming crews. Yeah. P equals V up. Right? The things you learned in high school, but you forgot them. Okay. P equals V up. So for the positive wave, P positive is positive. P negative, under this definition, is negative. Right? So under this definition, the negative propagating current amplitude is 180 degrees out of phase with the voltage amplitude. And therefore, its associated power is negative. So you have to think, does that make sense? It makes perfect sense. Because if you still remember, in your electric circuit textbook, in the very first page, it will tell you this book is using passive sign convention. Power is positive, means the power is wasted or delivered to you. So for type power, if it sends a positive traveling wave, it is losing power. But V times I is positive. So the positive power means it's losing power. From the generator, type power is sending this power to you. It's meant to be used by you. So type power is losing power. But that lost power takes on a positive sign. But if the user cannot use 100%, it returns some portion of the power back to the type power. Delivered takes on a positive sign, returned must have a different sign. So the power returned by the user to type power through the transmission line in the form of a reflected wave must have a V times I having a negative value. So the power returned or the power gained by type power must have a negative sign. Okay. So this is all taken care of in our derivation. So this is a completely valid result. Right? Remember, power delivered to someone to be used, the power is lost is positive, the power gained needs to be negative. So the reflected wave is like another small generator is sending power to type power, right? The power you cannot use. All right, so up to now, we are very happy. So through this relationship, we can somehow have, after introducing characteristic impedance, remember again, in characteristic impedance, it is the parameter intrinsic to the transmission line. Once you have a given transmission line, the voltage ratio for the positive propagating voltage to the current should be fixed. The backward voltage and current, they're also fixed, but only differing by a negative sign. Okay? So with the introduction and the understanding to transmission line, we only have V0 plus and V0 minus remain to be solved. So the number of unknowns is now reduced to 2. All right. Until now, you might be asking, you've been doing all this derivation in the frequency domain, in phasor domain, which I'm not very good at. Okay, so let's transform the result back to the time domain, which is completely possible, right? If you understand the definition, of phasor notation against the time domain parameter, so voltage as a function of space and time is a real part of the voltage phasor in the frequency domain as a function of space only, multiplied by exponential j omega t. Now, something you have to remember. V0 plus and V0 minus. These two amplitudes are usually complex numbers. Phasors usually have the amplitude and an associated phase. So I can somehow write V0 plus is having some amplitude and its own phase. V0 negative is having its own amplitude and its own phase. Okay? I substitute that back into the time domain. Eventually, this is what you have. In the time domain, you have an oscillating cosine wave propagating to the positive direction, and you also have a counter-propagating backward wave. It's also a cosine form. But having a phase difference might make it a sine wave. Okay? It really depends. Is this completely new to you? On the transmission line, you have forward propagating wave, backward propagating wave. Is that new to you? What is the result? Something that you know, everybody here knows already. If you have counter-propagating wave on the same medium, you will have standing waves. Right? So mathematically, you have cosine plus cosine. So yeah, we're going back to junior high. Cosine plus cosine equals cosine multiplied by cosine, right? So eventually in the time domain, you have a standing wave. You have a standing wave. We will come back to this aspect in more details in the next PowerPoint set. So let me try to stop here, and I'm concluding the first PowerPoint set for transmission line. Do you have questions? If not, I am going to continue into the second PowerPoint set, which is more heavily mathematically involved. So, well, it depends on whether you perform the preview before the class. So do you have questions before we move on to the second PowerPoint set? No question? How many students online? 42. Not bad. You're doing better and better. Okay, so switch to a new PowerPoint set. All right. Okay. So as you can see, the title of the second PowerPoint set is telling you we are trying to investigate into more details to a more simplified transmission called lossless transmission. So at this point, you have to think, what does lossless mean? Lossless means it's better, easier, right? And the professor is kind to you. or Professor is lazy because it's a simplified version. But when I talk about a lossless transmission line, what elements am I trying to omit? Lossless, if you remember. If I have loss, which lump elements are introducing loss? Resistors, right? So lossless transmission line means I have a very simplified model for the transmission line. I only have inductor and capacitor. Now, if you still remember, inductors and capacitors are energy storing elements. They store energies. They convert energies to electrical form or magnetic form, but they don't waste energies. All right? So by definition, if I'm now focusing on a lossless transmission line, my circuit model would only have inductors and capacitors. Which makes sense. Now, we understand the picture. Do we need to rewrite everything? Lossless transmission line. Do we have to derive, start from KVL, KCL all the way here? Spend another 60 minutes? Of course not. All we have to do is, as I said, for transmission line, everything is contained in the knowledge of gamma and characteristic impedance. Right? So, gamma in the lossless case, there's no loss, there's no resistance, no conductance. Simplified version. Characteristic impedance, simplified, right? I'm a very nice guy, I'm going to show you the results. Without loss, characteristic impedance is the square root of L prime divided by C prime. Right? Here, let me write it for you. Losses. Z0 is now L prime divided by C prime. Gamma. Gamma, by definition, there's no alpha. Right? There's no alpha. Alpha means loss. Now we're talking about the lossless transmission line. This has to be 0. Gamma is now omega L prime C prime. This is beta. Okay, purely imagine J, and that is equal to J 2 prime divided by O. Okay. So if we have a lossless transmission line, things become simplified. Okay, so the wave travel, there's no loss. So different geometries and different materials used to construct the transmission line will in turn change its propagation constant and its characteristic impedance. Okay? So the way I like to teach transmission line as a first topic for this course is throughout the entire semester, you will be able to derive the corresponding C prime and L prime, R prime and G prime. Okay? So we start with a target and we use the entire semester to understand it, to approach it. Okay. Now, let me try to think about it, okay? Because I tend to use, probably start from now on, I want to use the PowerPoint because the math derivations are very messy. Okay, so this is a recap of what we learned from the last 100 minutes. We only have 15 minutes left. So voltage phasor with a hat as a function of space is having a positive propagating amplitude plus this propagation form plus a negative reflected wave, right? And the current, by now, we know that the current amplitude is nothing more than the voltage amplitude divided by the characteristic impedance. Again, be careful. For the reflected current amplitude, it takes on a negative sign because you're sending the power back to the generator. It needs to have a negative sign. Okay. So now the question is, I have two equations. I have two unknowns. The number of unknowns is equal to the number of equations, which is okay. So I started with 4 unknowns. By introducing Z0, I have 2 remaining voltage amplitudes. So the number of unknowns is down to 2. So I should be able to acquire complete information now. So the process flow now really depends on your understanding. So I'm showing you a real system. I have high power, right? High power. I have a generator. The generator itself might have some internal impedance. And the power is delivered to us through the transmission line. And we, the users, are connecting, plugging our components into the outlet. And that component has its own load impedance, ZL, capital L. So try to link this picture to these 2 equations. Question number 1. Where do you want to define Z as 0? What kind of question is that? Doesn't matter, right? The equation is equation. Z as a function of Z can be 0 here or can be 0 here. I'm trying to ask you, in the past, we usually define Z equals to 0 at the input, right? For convenience, the input is 0, so this is maybe 10 kilometers, right? I know my distance. If you want to use Z equals to 0 at the input, where your generator is, which is also fine. But the trouble you run into is, if you want to know the voltage values or the current values at the load, V of L, L means the length of the transmission line. These exponential terms do not disappear. Then your mathematical derivation will be very, very messy. Okay. And the second reason is, why do we care about the voltage and current here at the load? Why? let me erase something here. Answer is, we know the load. The load is inserted into the wall outlet by us. That is a well-known parameter. So if you know the load impedance, ZL is, by definition, is V at the load divided by I at the load. But that is known. Right? Do you follow my philosophy? So on a transmission line, if I want to properly use a transmission line, I do care about how voltage and currents are changing along the line. But more importantly, I really care about the message or the information of the power delivered into the load. Right? That's the most important message I need. So I really care about the voltage at the load and the current at the load. But the voltage at the load divided by the current at the load is determined by my load impedance, which is defined by myself. So you really, these equations should be using Z equals to 0 at the load. Think about it. What's the benefit? If I define Z equals to 0 at my load, V of the load, meaning Z equals to 0, exponential terms are all ignored. Right? Exponential J0 is 1. Right? So all these four unknowing components are replaced by 1 at the load. So be careful and look at this definition. Okay? Usually, although we want to define Z equals to 0 at the end, at the input, but here in this particular case, from now on, we are going to define Z equals to 0 at the load. And we are trying to solve everything at the load and walking back or tracking the answers back to the input. So for this reason, I'm trying to define a new distance variable. So Z is 0 at the load and possibly going in the direction from left to the right. But at the same time, can I also define a new distance variable as D? D is 0 at the load as well, but it is positive going back to the generator. Okay? So this is saying I am defining this D equals negative Z, which is fine. Right? So let me repeat myself again. For simplicity, for convenience, I want to analyze the system with the load with a value of Z equals to 0 and D equals to 0. Z is pointing from the left to the right. D is pointing from the right to the left. The only difference is the direction. Okay. So D equals to negative Z. Okay, so now we are capable to start the analysis. How much time do we have? 6 minutes, maybe enough, maybe not. So what I know is VL, the voltage at the load, is V of 0, right? Z equals to 0. So this is directly V0 plus V0 minus, right? IL is I at 0. This is Z0, V0 plus minus, right? Now you can see why I want to define Z equals 0 at the load, because mathematically, very simplified. Okay, so Z load is VL divided by IL, which is, well, you have to perform the division. V0 plus V0 minus V0 plus minus V0 negative times V0. Okay. Remember, what are we trying to do? We are trying to solve for V0 plus and V0 minus. Does it help to further reduce the number of unknowns to just one? Look at the equation. If you look at this equation, at the load, we have this mathematical equation, but does it also tell us once we connect the transmission line to a known load, we already know the ratio between the reflected voltage and my input voltage. Okay, so let's do it. So I'm trying to multiply this thing to the left. So ZL. So this is the equation I want to use. I want to use this fact. Having any reflection is because of a load. So at the load, with a given load, I determine the amount of reflected wave. Okay. So using this, I can get that around V0 plus is ZL minus negative. So this is what I have. Using the knowledge and defining Z equals to 0 at the load, I somehow realized my reflected voltage amplitude is directly determined by the difference of my load to the characteristic impedance of the transmission line divided by their sum. So this is further telling me, hey, everything is even more simplified. Having the load connected to the end of the transmission line, I can somehow relate V0 minus to V0 plus with a known reflection coefficient. This gamma V is called a voltage reflection coefficient. Then, the entire system can be solved just by knowing what the forward voltage amplitude is. And everything's being solved. Okay? So think about it. We started today from KBL, KCL, writing down a lot of equations. Eventually we have 4 unknowns. But then we found out the transmission line has this beautiful characteristic. Voltage divided by current for certain propagation direction will be a constant. Maybe positive, maybe negative. Then we can reduce the number of unknowns to 2. And then at a load, we can further relate the backward voltage amplitude to the forward voltage amplitude by a reflection coefficient. Then we only have to solve for the positive voltage amplitude. So we spent 100 minutes to arrive at this point. So on Wednesday, please do review the materials. Please. On Wednesday, we will encounter even more mathematical derivations. But again, like I said, I want to emphasize on physical meanings. Okay? So on Wednesday, I tend to use a PowerPoint. Maybe I won't be writing so many equations on the board. You can look at the equations on the PowerPoint, but try to understand what the derivations mean in physics. Right? So on Wednesday, we will understand, we will be able to solve for the transmission line completely. And maybe if time allows, we are going to talk about the particular loads. What do particular loads are going to affect the resulting voltage and current behaviors along the transmission line? All right, so let's stop for today.有问题吗？有没有同学问问题 ？Disappointing。
我这学期只教4个学生，我教到